ringed planet Saturn. More than 100 times the mass of Earth, its metallic core lies beneath 80,000 kilometers of liquid hydrogen and helium. It's called a gas giant. Saturn is orbited by at least 62 moons, each unique, some with complex and dynamic environments. Our only detailed examination of the Saturnian system ended in 2017, when the Cassini probe was intentionally crashed into the planet's dense atmosphere to guard against accidental contamination of the moons. Viewed from Earth, Saturn's rings are visible, but not in any detail. They were thought to be solid, until mathematical analysis suggested they were orbiting particles. But how did they get there? And why was Saturn alone in having rings? In the early days of space research, Saturn was just too far away. Conventional rockets could only just reach Mars. In 1964, NASA realized that a space probe launched in 1977 could take advantage of a rare alignment of the outer planets to fly past all the gas giants. Using gravitational assistance from the planets, it would just be possible with the technology of the day. An ambitious new mission began to take shape. It was dubbed the Grand Tour. Two probes that were far in advance of anything yet attempted would be part of the Mariner series. Because no spacecraft had been sent beyond Mars, mission planners felt it would be wise to send two rudimentary advanced probes to Jupiter and Saturn to test the deep space environment. Researchers didn't know if it was even possible to cross the asteroid belt between Mars and Jupiter. In 1972, Pioneer 10 was launched towards Jupiter, and the following year, a twin, Pioneer 11, was sent to Saturn. Both craft passed by Jupiter and discovered that the electron radiation there was 10,000 times as strong as at Earth. This was a surprise to engineers at NASA, who had to modify the more sophisticated craft they were preparing for the Grand Tour. The probes, being built at NASA's Jet Propulsion Laboratory, were part of a program known as Mariner Jupiter-Saturn, but this was soon changed to the Voyager program. They were launched 16 days apart in late 1977, while Pioneer 10 was heading toward interstellar space, and Pioneer 11 was still 2 years away from Saturn. In 1979, as Pioneer 11 approached the ringed planet, it began sending back pictures far clearer than anything seen before. A new ring, the F ring, was observed for the first time. The craft flew by Saturn, passing beneath the rings. Mission planners were uncertain how broadly the ring particles spread. If there was a threat to the spacecraft, they were prepared to sacrifice Pioneer 11 to get a clear idea of the environment they would encounter with the following Voyager craft. The probe passed the rings safely and continued beyond Saturn into interstellar space. NASA received its last communication from the probe on the 24th of November 1995. The following Voyager 1 and 2 probes were very robust, designed to survive for a very long journey and with far greater technical capacity than the Pioneers. In late 1980, Voyager 1 approached Saturn. Although its high-resolution polarimeter had failed, it was still able to see a new ring, called the G ring, orbiting 100,000 kilometers above Saturn's cloud tops. For the first time, researchers could see how the rings moved. Uneven features within the rings were called spokes. They're transient and are thought to be particles lifted by an electrostatic charge. After such a long preparation, information was now coming into JPL at such a rapid rate that the planetary scientists were overwhelmed. Saturn's moons were of great interest. Voyager 1's path had been chosen because it would take it close to Titan, the solar system's second largest moon, and the only one to hold an atmosphere. But the images were disappointing because the thick atmosphere of methane and nitrogen was impenetrable. Voyager 1 now looped up above the solar system on a trajectory that would take it to interstellar space. As it looked back at Saturn, it captured one last image from a unique angle. It was almost 10 months before Voyager 2 neared Saturn. Its different path meant that it could continue on to Uranus and then to Neptune. Its high-definition camera was still working, and planetary researchers were expecting detailed pictures of the rings. They were not disappointed. The varying densities and spacing within the rings was more complex than anyone had expected. The rings are named for letters of the alphabet in the order that they were discovered. It became apparent that the rings had changed in the time since Voyager 1 had seen them. Though they stretch from 7,000 to 80,000 kilometers above Saturn's equator, their thickness is on average just 30 meters. The spacecraft also returned pictures of the moon Enceladus. Its cracked, uncratered surface was made of ice, below which is an ocean. Ultimately, Voyager 2 left Saturn. Unable to go into orbit, it sped on toward Uranus. It would be 23 years before another probe visited.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
Launched in 1997, Cassini was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. It would take more than 6 years to reach Saturn. Cassini was the biggest, most complex interplanetary spacecraft yet devised. Its 12 different instruments each had a dedicated team of research specialists on Earth to interpret the data it sent back. Its high-gain antenna was used for high-speed data relay back to Earth, but in what's called a ram maneuver, it was sometimes used as a shield to protect the spacecraft from debris impact, especially when crossing the plane of Saturn's rings. On the 1st of July 2004, it fired its engine to go into orbit around Saturn. It was designed not to fail. Beside its main engine was a backup, in case the primary engine did fail. It had 16 monopropellant thrusters, 8 prime, and 8 more, also as backups. In mission control at the Jet Propulsion Laboratory, the engineers could not know what was going on. The time delay and Cassini's disappearance behind Saturn meant that much of the telemetry was recorded for later replay back to Earth. The engine burn lasted for 106 minutes. Cassini was the first probe to employ a solid-state recorder, unlike the earlier Voyager craft that registered data on a mechanical tape recorder. Cassini's first orbit followed a highly elliptical path that would take it out past the moon Titan. This was important for two reasons. Its gravity would be necessary in modifying Cassini's course, so Saturn and its other moons could be observed from different perspectives. Secondly, Titan, with its dense atmosphere, was targeted as an area of major interest for the Cassini team. The European Space Agency had built a small craft called Huygens, attached to the side of Cassini. On its second approach to Titan, the Huygens probe was released. It was equipped with a heat shield, a parachute, and enough battery power to last for several weeks. Over a 20-day period, Huygens drifted for 4 million kilometers. It would transmit data back to the orbiting Cassini, which would later relay it to Earth. 3 days after separation, Cassini made a course correction that would prevent it colliding with Titan. As Huygens reached Titan's atmosphere, Cassini was coming around for its third close approach of the moon, ready to receive signals from the lander. While it drifted to the surface of Titan, Huygens sampled the atmosphere and recorded images of the landscape. Pictures from beneath the clouds revealed low hills and channels cut by flowing liquid. There were few impact craters, and those that existed were heavily eroded. It was the first landing on a body in the outer solar system. Images from the surface showed weathered rocks made of water ice. What surprised everybody was that Titan is a geologically active world, where liquid ethane and methane, rather than water, have carved the features. As Cassini continued looping out around Titan, it used radar to map the moon's surface, confirming the widespread distribution of hydrocarbon lakes. The probe discovered that rain fell on Titan, but it was a mixture of liquid ethane and methane. The moon has weather and other erosive forces similar to Earth, but the chemistry is radically different. The small moon Enceladus drew attention to itself as the whitest, most reflective body in the solar system. Its surface shows cratering in the north, but the south has giant cracks known as tiger stripes. On Cassini's first loop past Enceladus, the magnetometer team noticed an odd deflection of Saturn's magnetic field, as though the small moon had an atmosphere. During its second pass, the team noticed the same phenomenon. They asked for the next traverse of Enceladus to pass much closer, so Cassini's course was modified to fly just 175 kilometers above the icy moon. The probe passed through a plume of water vapor emanating from the tiger stripes. It contained common salt. In all, Cassini made 24 swoops past Enceladus, with the closest approach flying just 25 kilometers above the surface. Each one of the probe's instruments gathered different evidence about the jets of water expelled through the cracks in the moon's south. On Mars, rovers have been combing the surface looking for traces of life, but Enceladus was flaunting remarkable signs. Gravitational analysis revealed a liquid ocean beneath the ice, and infrared detectors saw heat emanating from the cracks. As well as salt, the science team discovered traces of silica that can only dissolve in hot water. Hydrogen and organic compounds were also detected.
We know from Cassini that Enceladus has a global ocean, so you have water. We also know that there are organics coming out because they've been directly measured, both in the gas and in the particles. We also know there's a source of energy. The South Pole was hotter than the rest of Enceladus. And then we found evidence that deep inside, there are hydrothermal vents on the seafloor of Enceladus. So these hydrothermal vents would supply the heat and the nutrients that could possibly support life.
With a diameter of 500 kilometers, Enceladus is just too small to sustain a hot core via radioactive decay. Gravitational squeezing by Saturn explains some of the heating, but the source of the high temperatures detected remains a mystery.
But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. And you know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet.
In the Earth's deep oceans, hydrothermal vents provide the warmth and nutrition to support life. They may even have been important for the origins of life. Planetary biologists are speculating that the environment in the oceans of Enceladus may be the most likely place in the solar system to find some sort of extraterrestrial life. It took a while for Cassini to be in a position where backlighting from the sun allowed the imaging team to capture pictures of the plumes. Using a similar technique, the imaging team took this picture with Saturn directly between Cassini and the Sun. It reveals Saturn's E-ring, the hazy outermost ring that is usually very difficult to see. The E-ring is a result of the plumes from Enceladus and is constantly replenished by the saltwater eruptions. Saying that Saturn has 62 moons is misleading. Each particle within the ring system could be regarded as a moon. There are the inner large moons and the outer large moons. There are the shepherds that shape the rings. There are co-orbitals that exchange orbits. And there are even moons that orbit other moons. All are unique. During the Voyager missions, interest in the moons came as something of an afterthought. But for Cassini, close examination of the moons was planned from the beginning. Iapetus orbits Saturn beyond Titan. It was first observed in 1671 by Giovanni Cassini. He could see it as a dot of light to the west of Saturn, but could not see it when it should have been to the east. Iapetus has one bright face and one dark one. Because the moon is tidally locked to Saturn, it is always the dark face that leads as it orbits. One theory suggests that it sweeps up debris that spews from Phoebe, a more distant moon. Another feature of Iapetus has scientists baffled. A ridge along the equator stretches more than halfway around the moon. It's twice as high as Earth's tallest mountain. With Iapetus being just 1,500 kilometers across, the ridge gives Iapetus the appearance of a walnut. Very accurately directed bursts from Cassini's main engine allowed mission engineers to modify the probe's looping orbits so mission specialists could focus on various moons, different areas of the ring system, or different parts of Saturn itself. With gravitational assistance from the moons, particularly Titan, mission control were able to conserve fuel. The Cassini probe performed so well it received 2 mission extensions, but the fuel could not last forever. Planners had scheduled the most hazardous part of Cassini's mission for its final year at Saturn. Late in 2016, Cassini began a series of polar orbits that would take it close to the outer edge of the rings. In what mission specialists called grazing on the rings, the craft's mass spectrometer and its cosmic dust analyzer would sample particles and gases as it crossed the ring plane. In orbit 251, its first pass above Saturn's North Pole, it recorded the peculiar hexagonal storm that was first hinted at by the Voyagers. The storm, more than twice the diameter of Earth, maintains its hexagonal shape, but its color changed with the advance of summer. At its center is a cyclone, shown here in false color, with red indicating lower cloud and green higher cloud. Winds at its edge blow at 540 kilometers per hour. One part of Cassini's dual-technique magnetometer had stopped working early in the mission. Without it, the craft had to do roll maneuvers from time to time to calibrate the instrument. The spacecraft would make 20 ring-grazing orbits, with the work of its instruments mapped out to the second. As the Sun was almost directly behind the rings, Cassini looked for dust clouds. Something is reducing ring particles to fine powder. Cassini made a number of radio occultation observations. With the rings between the spacecraft and Earth, 3 radio signals of differing wavelengths were transmitted simultaneously, allowing the radio science team to build a profile of the ring particles. This false color image of the A ring, the outermost of the large bright rings, shows red for particles larger than 5 centimeters across. Green denotes particles smaller than 5 centimeters, with blue for particles smaller than 1 centimeter. The complex gravitational interaction between Saturn, its rings and its moons leads to gaps in very particular places. Before Cassini arrived, only 18 moons were known. That number has grown to 62. Prometheus acts as a shepherding moon, limiting the inner edge of Saturn's F ring. Along with Pandora, which orbits outside the F ring, the 2 moons keep the ring narrowly confined. In April 2017, Cassini's orbit was changed for the final phase of its mission. The probe would now loop inside the rings. Though it would ultimately mean burning up in Saturn's atmosphere, the information gathered from such close proximity to Saturn and its rings would give a fuller picture of the gas giant. It was decided that intentionally destroying Cassini was preferable to letting it drift without fuel, possibly contaminating one of the moons. Cassini's sensors began picking up a stream of ring particles raining down upon Saturn. A continuous shower of ice and dust particles are dragged toward the planet's equator by gravity, or at higher latitudes, charged ring particles spiral in along magnetic field lines. Every second, 10,000 kilograms of ring rain falls to the surface. At this rate, the rings will be completely gone in 100 million years. Researchers were surprised to discover an electric current flowing between the inner D ring and the upper atmosphere. Toward the end of Cassini's close passes of Saturn, the spacecraft began catching the upper edge of the atmosphere. All information had been retrieved from the recorders. Data now was transmitted directly back to Earth, but it relied on the spacecraft's thrusters to stop Cassini from tumbling, keeping its high-gain antenna pointed accurately. The probe's final work was sampling the atmosphere and measuring the offset of Saturn's magnetic axis.
This is ACS-1. We just had transition to high rate mode.
In mission control, there was no more control. The engineers could just monitor the signal sent from Saturn 84 minutes previously.
The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft.
It will take years to process the data gained from Cassini. As yet, there are no future missions to Saturn scheduled.
Thank you.